Q, we of course have to use the appropriate type of heat capacity, which is the isochloric heat capacity. So if you compare these two expressions, what's left over, there are two common terms on both sides, N and delta T, so N and delta T, so the rest must be, of course, CV, and that's what we came up with. CV is F over 2 times R. So that is the molar heat capacity at constant volume. If there is no potential energy term, we'll introduce the potential energy term later. So that's what we're going to be learning. We haven't learned yet how to count F, so we'll be doing that today. Other things I'll be using, of course, if I ever want CP, you just add R to the CV. Remember, this is on the molar heat capacity side. And then if I ever do want to talk about the specific heat, again, I just take the molar heat capacity, capital C, divide by the molar mass, and I get lowercase c, which is my specific heat capacity. So again, this here is in joules per mole Kelvin, whereas this is in joules per kilogram Kelvin. So to swap back and forth between kilograms and moles, I just need how many kilograms per mole. That's the molar mass down here. Also, I talked about gamma. Gamma is the ratio between Cp and Cv. So we'll mention that. Obviously, if you're talking about a gas here, by necessity, it's greater than 1. So, using all that background, that's all stuff we introduced last time. Let's now start talking about how to count degrees of freedom. So let's start with a monatomic gas. A monatomic gas is one in which every gas particle is a single atom. So one gas particle equals one atom. So what we literally have flying around are individual atoms. They look like that. So for a monatomic gas, let me take one of these. Let's say this is one atom. It has 3 degrees of freedom. It can move up or down, left or right, front or back. 3 spatial degrees of freedom. Okay? That's the only thing that it can do. Okay? Atoms are negligible size, so there's nothing really to rotate of them. Okay? So the degrees of freedom it has are to move in the 3 spatial dimensions. Okay? So F equals 3, what we call them translational degrees of freedom. It can basically move in 3 spatial dimensions. Okay? So how many different ways a particle can move is going to tell us what is the specific heat. Okay, so this tells us that, let me make sure I get the number here, CV is equal to 3/2 R, which comes out to be, if you multiply in the ideal gas constant, 12.47 joules per mole Kelvin. What I am saying is that any monatomic gas, it does not matter what it is, has this molar heat capacity. That's a bold claim that any gas, no matter what it is, no matter what kind of atom that gas particle is, as long as there's only one atom in each gas particle, I'm saying this is the value. So that's a powerful thing. Of course, maybe I should put down Cp as well. Of course, then I just add R to it. So that's going to give me 5/2 R. And that will be 20.78 joules per mole Kelvin. All right? And if you wanted to compute gamma, the ratio, again, it's still unclear what this is good for, but we'll find that it has use later, so we might as well compute it now. We'll divide 5/2 by 3/2 R. R's cancel, 2's cancel, we get 5/3, which is approximately 1.67. All right. So this is my claim for any monatomic gas, let's now compare against real results, okay? So let me give you two monatomic gases, two noble gases. So you may know a noble gas, right? These atoms don't like to combine with other atoms, so they're not going to combine with each other, okay? That's why each atom just stays its lonely old self, okay? So here is my chart where I'm going to start. I'm going to give you the element. These are elements that form monatomic gases. So that they form monatomic gases. I don't want to include elements that don't actually do this kind of behavior, because then it's obviously not going to make any sense. And I'll give you two, helium and argon. Okay? Two noble gases. Okay? There's a periodic table here that's nice and handy. It's all the stuff that's down the far right. Is this knowledge of chemistry that how many people here know what a noble gas is? Okay, great. Okay. So, let's talk about Z, which is the element number. It's also the number of protons in the nucleus. Yes? That's how you judge what something is called. I hope this is common basic science knowledge. I don't know if you call it Z, but you look over there in the upper right corner, helium is 2, argon is 18, okay? Element number 2, element number 18, okay? All right. So, what is the molar mass? How many, and I'm going to put this in non-SI units, grams per mole, so be careful there. For some reason, when you're a chemist, you like to work in grams, but it's not SI, so be careful. So this often is available on the periodic table. You can always look it up if you have a crappy periodic table that doesn't have these. This is about 4 grams per mole, and this is 40. I don't know if those are the super most accurate, but they're pretty close. And I want to point out that this is about 10 times this. Okay, in fact, exactly 10 times this. Okay. You might also notice that there seems to be a pattern here that going from here to here, going from the element number to the grams per mole, is a factor of about approximately 2. That is not an accident. Okay? Those of you that may know how a mole is defined, that's pretty much expected. Here's why. First of all, you guys know what a nucleon is. Anything in the nucleus? Protons and neutrons? Okay? Protons and neutrons. Okay? Now the amount of nucleons per atom is very close to, I guess I should say approximately, for those of you who studied more advanced chemistry, it's approximately equal to the grams per mole. Okay? So how many protons and neutrons you have total in the nucleus is related to the amount of grams per mole. Now, what is it called when a given element has different amount of neutrons? Do you guys know this? Isotope, right? That's right. So there are different isotopes, right? Okay. So there is some variation, but if we take the most common, that's basically what we're going to be talking about. But the whole idea of why a mole is defined the way it is to make this true. Okay. So the definition of a mole is, what is moles for? It's a way to go from the small scale to the large scale. So instead of working with nucleons per atom, we work with how many grams is that per mole of those atoms. It's a way to basically link the tiny to the large. Okay? So basically, you should know that for light elements, the number of protons is approximately equal to the number of neutrons for the most stable isotope. All right? Now, as you go up to the very heavy elements, this starts to not be quite true. You need more neutrons than you need protons because the neutrons are the peacemakers. The neutrons keep the protons, which are obviously like charge, from flying apart. So, but for light elements especially, and approximately true even for heavy elements, you will find that the number of protons and number of neutrons is about the same. So we talk about helium. It has 2 protons and about 2 neutrons. Hence, there are 4 nucleons per atom. Hence, there are 4 grams per mole. Okay? Same thing here, right? The most stable isotope of argon has 18 protons, and it has around that, it's, what is it, 22 neutrons, okay? So this is 2 protons plus 2 neutrons. This is 18 protons and 22 neutrons. And what do they add to it? It adds to 40. So there are 40 nucleons per atom, hence it's 40 grams per mole. Okay? So if you're noticing that there's a pattern of a multiplier of 2, that's just making sure to fold in the fact that you also have neutrons, right? Does that make sense? You will not be far off if you don't have a periodic table on you. If you need to guess the molar mass of something, especially a light element, just take the number off the periodic table, the element number, multiply by 2, and that's probably going to be pretty close to the molar mass. Okay? Does that make sense? Okay. So that's just a little bit on chemistry. So let's go ahead and calculate, based on our model, what is going to be the specific heat. And for some reason, I can only find values to compare to CP, so I'll have to do joules per kilogram Kelvin. So let's find out what we get. So I am claiming in our model that both helium and argon, because they are monatomic gases, are 20.78 joules per mole Kelvin. That is my claim. If we're on the mole side, we're saying there's no difference. However, 1 mole of helium and 1 mole of argon have different masses. So what that means is, if you have 1 kilogram of helium versus 1 kilogram of argon, you're not going to have the same moles, right? You're going to have many, many more particles of the lighter helium and just a few of the argon, because each argon is just more kilograms. So let's go ahead and calculate here. We're going to divide that common C, which I said was this on the mole side, and divide by this molar mass, and I'm going to get very different results. Now, when you do that, make sure, of course, that you throw in a factor of 10 to the negative 3 on this, because this is not SI, right? This is not kilograms per mole. So if I want to get kilograms from grams here, it's going to need some adjustment. Let me tell you what you get. You get 5195 over here, and here 519.5. So notice that all the commonalities that we have just got kind of washed away Not because they weren't the same on the moles per Kelvin, or the mole side, but because now we're on the kilogram side. This is about approximately 1/10. In fact, exactly 1/10. So what we found here, grabbing this formula here, they had exactly the same molar heat capacity, but because the argon has such a higher molar mass, in fact 10 times, the specific heat was 1/10. Does that make sense? So I mentioned earlier that if you're thinking about the mole side, there's a lot of commonalities. If you're only thinking on the kilogram side, you totally miss it. So what this says is that when we're talking about 1 kilogram of argon, it has a much smaller heat capacity because there's just less atoms to absorb energy. One kilogram of argon is not that many argon particles. And so there aren't as many ways to spread that energy thin. And so this is going to have a smaller heat capacity, less thermal inertia, and so it's going to be a lot easier to raise the temperature of this. Okay? If we had 1 mole of each one, not just 1 kilogram of each one, but 1 mole of each, we'd find that it takes about the same. Okay? So that's just our model. Let's actually go to the lab. So the actual experimental value of this, I guess I should have put this as the common header. One is our model, one is the actual. This comes out to be 5193, and this is 520.3. It's pretty good, right? Obviously it's not exactly there for some more subtle advanced effects, but it's a pretty good model, isn't it? Really close. Does that make sense? Question?
How do you get the numbers in? What formula?
This formula right here. So I took this, 20.78, and I divided by this in kilograms per mole, not grams per mole, because I wanted the kilogram here.
Okay. Thank you.
So it would be, this number came from 20.78 divided by 4 times 10 to the negative 3. So that's this. Any other questions?
And you said you got molar mass by dividing the moles by the element number.
Pardon? Say it again?
How did you get the molar mass if you don't know the periodic table again?
Just take the element number, well, that you need a periodic table for, if you don't remember. But if your periodic table isn't very good and doesn't have the molar mass, your best chance is to multiply the element number by 2. That's grams per mole. The reason is it has, again, 2 protons, that's what the 2 is. And it's liable, the most stable isotope is liable to have about the same number of neutrons. So you're basically doubling it, because the nucleons contained in each atom is basically the grams per mole. Okay? Some of you may know that it's the mole is specifically defined as 12 grams of carbon-12, right? So it varies a little bit, so that's why they have to use one element to do it. The reason why is that some of the mass is actually turned into energy in the binding, right? Good old E equals mc squared. Is this all stuff that you talked about? Maybe not.
We talked about it in
Okay. So, all right. So let's do the next order of business, the diatomic. Clear some space. Diatomic gas. This is where each gas particle equals 2 atoms that are bound together. So, kind of do like this, flying around every which way, like so. So let's talk about this. We have each gas particle looks like this, flying around. So obviously it still has 3 spatial dimensions to work in. So F equals 3, so you've got your translational. That's all there was for the monatomic gas, but now there are more degrees of freedom. Okay? The next degree of freedom, the other place you could put in energy is not in flying around in the 3 spatial dimensions, but rotating. We've learned about rotational kinetic energy. So the question is, how many of those do we have? We could potentially rotate around all 3 spatial axes, right? X, Y, and Z. So one way is like this, one way is like this, but we have a little surprise. This one is negligible, okay? Remember that these atoms have negligible size, so there is no third axis, okay? So there are only +2 rotational degrees of freedom. We say that the third axis is degenerate. So there is really no contribution from that third one. So that brings us up to a total of 5. But wait, there's more, okay? So we also get into vibrational degrees of freedom. So this thing can vibrate like this. That's another way that it could have a degree of freedom, right? So when we say degrees of freedom, we just mean different ways that you can actually move, okay? Because these are different places where you can soak up energy, okay? Does that make sense? Okay, so we have +1 vibrational for a total of 6. And that's the first time that we have actually engaged the fact that there's a bond between them, right? The other ones don't care that there's a bond between them, but this one, well, I guess the rotational one, they have to stick together, but we haven't done anything to that bond. This one is the only one where we're actually compressing the bond, right? That vibrational degree of freedom. And we know, if we model this as a simple harmonic motion, we basically know that when you're in simple harmonic motion, you're trading kinetic energy for potential energy, right? So this is going to be where we finally have potential energy kick in, okay? So the vibrational degree of freedom and has a potential energy associated with it. So that's where we finally have potential energy kick in. Now, how much is it? Well, I hope it's not surprising to you that if we talk about the average kinetic energy, the average potential energy is the same because energy conservation, right? So basically, think of that extra potential energy as just an extra energy term, kind of a value-added energy term that you get. So first I have to tell you something. If you're tempted just to put F equals 6 into the equation, you have to know that you don't get all of these at once. So quantum mechanics tells us that these will gradually be added. They can't all be accessed. It's like rungs of a ladder. You cannot access them all at once. So in fact, when you're at low temperatures, the other degrees of freedom are quote unquote frozen out, and you only have translational. Then, as you climb towards medium temperature, so oftentimes room temperature that we work at is in this realm, and then only when you get to very high temperatures do you get to access all of these degrees of freedom. They kind of gradually get blended in as you go to a higher temperature, okay? So let's predict what we're going to see. At low temperature, we have exactly the same thing as before. So there's no difference in low temperatures. But for medium temperatures, we have to put in a 5 because we have unlocked the levels of translational and your 2 rotational, okay? So no big deal there, hopefully. I should mention that oftentimes the temperatures that we live in and work in are in this realm. But we should reevaluate what happens at high temperature because, of course, we have this extra little hiccup where we have a potential energy term. So what do? We go back over here and we see what are we supposed to have done differently. Well, of course, we need to make sure to add in this potential energy term. So energy is kinetic energy plus potential energy. So we get F over 2 nRT for that. And then we just get an extra one. So we get an extra energy term. So that potential energy is associated with one of those degrees of freedom, right? So we don't put in F in the next one. Only one of those degrees of freedom had associated with it a potential energy, right? So we had 5 that contribute kinetic energy, plus a 6 that contributes kinetic energy, plus an extra potential energy, right? So we put in F equals 6 here, and then one of those has an associated potential energy, right? Now before I put in the 6, let me point out that the energy formula looks like this. So there's that extra +1 to indicate that one little extra potential energy, okay? So this is for diatomic gases at high temperatures, okay? So that's the only time you have to worry about the +1. Otherwise, the +1 isn't there. But the +1 indicates you get a extra bonus little energy from the potential energy. Does that make sense? So what do we get? If we put in our 6 here, F equals 6, we're going to get E equals 7/2 nRT, and yada, yada, yada. This leads to a CV of 7/2 R. Again, how do you do that? You just work it down like I just did right here. Questions?
It feels like to me that you're kind of double tapping your energy, where you have you're already accounting for your high temperature by saying that the degree of freedom is 6, and then you're adding another one. So that to me kind of doesn't make any sense.
Right. So that comes down to how the equipartition theorem works. So again, that's a little bit not something we should discuss here. So you have to include all these different energies. I guess the way to think of it is that the moment that you have an average kinetic energy of this, you will also have some potential energy on average. So you're not actually double counting, you're just acknowledging the fact that you're not talking about when you're at maximum kinetic energy and no potential energy or something like that. We're talking about averages. So if you have an average amount of kinetic energy, you will also on top of that have an average amount of potential energy. Does that sort of answer it? Okay. So we get to high temperature, and you get 7/2 R, okay? So common mistake is to think that there are 7 degrees of freedom. If they're not, there are 6. The reason why it's 7 and not 6 is because they get that extra little potential energy term. So we can make a little graph here. What would this look like? This is the first time we've had to acknowledge the fact that which heat capacity you should be using depends on what is the general temperature range in which you're operating. So it goes like this. So this is 3/2 R, 5/2 R, and 7/2 R. And this right here is your medium temperature plateau. And then you can see that there's a sharp increase as you step between the plateaus as these other levels are unlocked. Now, how long are these plateaus and where do they start exactly? That is a highly dependent thing. We're not going to touch that for the most part, we're just going to assume that we're squarely in one plateau or another. Okay, so we're not going to necessarily worry too much about the fact that where these transitions occur. So I know it's super vague to say low, medium, and high temperature, and that's purposely vague because where these plateaus start and end really depends on more complicated factors. So I will just say that for the most part, we will be working in the medium temperature range. So unless otherwise specified in the problem, you can assume that that's where we are, okay? Are there any questions on that? Okay, so again, let's try to test it out here. Of course, I should make a, I forgot to mention the CPs, I guess. So the CPs, so CV, if that's 3/2, let me make a little chart here. 3/2 R, 5/2 R, and 7/2 R. Then CP is, of course, we just add R to each one of those, right? So this will be 5/2, 7/2, and 9/2. And then the gamma will just be the ratio, so it'll be 5/3, 7/5, and 9/7. Notice, by the way, that as the CV increases, the gamma value decreases. Okay? It's not hard to show why that is. If you go over here to our original formula for gamma, that's CP over CV. That's equal to CV plus R over CV, which can be simplified. So another way to write it is like this. Hopefully you can see that they're inversely related. Okay? So as CV increases, gamma decreases. Again, what is gamma good for? We'll find out on Wednesday. But for right now, I want to kind of plant the seeds of what these values actually are. All right, so let's try it out, okay? Let's try it out and see how our model fares with real experimental values of these things, okay? Are there any questions before I do that again? All right, so let's do it. So let's take an element that actually behaves in this way. These that actually form diatomic gases. So I'll give you two. Hydrogen forms a diatomic gas. Every gas particle is two hydrogens bound up together. I'll give you another one, nitrogen. Okay? So what element is this? Element is, this is number 1, and this is number 7. What is the molar mass of these things? Grams per mole. Well, the grams per mole is going to be here. You remember I said multiplying by 2 is a good rule of thumb. It doesn't work for hydrogen because you don't need a neutron in the nucleus of a hydrogen. What's the nucleus of a hydrogen atom? 1 proton. So does it need spacers to keep it not as angry at other protons? No. Okay. So there, we basically get 1 proton and 0 neutrons. So that's 1 nucleon per atom, and so about 1 gram per mole. The fact that it has a little bit of round off, or it's not exactly 1, is because the mole is defined through carbon-12 and not hydrogen. Okay. All right. So what's in the nucleus of nitrogen? It's basically has 7 protons and 7 neutrons. So there we have it, 14.01 grams per mole. So, I am making a bold claim that if, let's say we're working in medium temperature, that CV is the same for both of these gases, okay? And the only reason we'll see a difference on the specific heat side is simply because of the molar masses. This is about 14 times this. So we should expect that the heat capacities are 1/14. So the heat capacity of nitrogen is 1/14, okay? So we wouldn't notice any difference if we were working on, or we wouldn't notice the commonality if we were working on the kilogram side. That's why we move to the mole side, because that's where all the commonality is, right? Now there's a little bit of an issue here that I need to resolve first, okay? And that issue is the fact that the periodic table is telling you one hydrogen, okay? Not what we have, which is 2 hydrogens. Okay? So we have to recognize the fact when we say we have n moles of gas particles, we do everything in terms of gas particles. Well, that means you actually have 2n moles of actual atoms. Okay? If each gas particle actually contains 2 atoms, right? We talk, when we say N and PV equals nRT, what we mean is moles of gas particles. What this is actually telling us is grams per mole of atoms, okay? So this is mole of atoms. In fact, I'll label this real quick here, M sub A. So M sub A is what you get off the periodic table, and for good reason. The periodic table does not make judgments about how these are going to combine with other things, even themselves. So you can have solid or liquid helium. I can't remember if you can have solid helium. You can definitely have liquid helium, okay? So what we need to actually do is go to our grams per mole of gas particles. So this is what you need to use. I will generally try to give you this already on the problem, but I will try to be specific in saying what is the molar mass that I'm giving you. What you really need is grams per mole of gas particles. So what I'm going to have to do here is I'm going to have to multiply by 2, okay? So I'm going to have to multiply by 2 because, of course, the mole of atoms, well, the gas particles each have 2 of those things. So multiply by 2 here. The molar mass that we need is actually 2 times the atomic molar mass. So this will be 2.016 grams per mole, and this will be 28.02 grams per mole. Okay? Does that make sense? Okay, so now we're ready to go ahead and do our calculation. So this is what I'm getting. I'm getting Cp, that's lowercase, in joules per kilogram Kelvin, and I will compare our model to the actual experimental results. So try these yourselves. Again, remember when you're dividing, what are you dividing? First of all, we're at medium temperature. So we're saying that CV is 5/2 R. So start there. And then you're dividing by this column. And remember to throw in a 10 to the negative 3, so it's kilograms per mole. Okay? So if you do that, the results you should get is a very high value for hydrogen, 14,427. And then for nitrogen, 1038. And again, what do you notice? It's about 1/14. They're the same on the molar side, and then the reason why nitrogen gas has 1/14 the specific heat is just because of the difference in molar masses. Okay? So let me give you the actual values. It's 14,296 and 1040. Not bad. Okay? So this simple model is really close to the correct answers. All right? Are there any questions on that? So again, counting degrees of freedom, you have 3 translational, 2 more rotational, for 5 total. Normally that's where we're at when we're at medium temperature. At high temperature, you get another one more, and it has an extra potential energy thrown in. Question?
What is lowercase cp?
It's the specific heat capacity at constant pressure. So remember we talked about can have molar heat capacity, or you can have specific heat capacity. One is for moles, one is for kilograms. You can, if you have a CV and a CP, you can have a CV and a CP on both sides, right? Both on the molar and the specific heat side. Now, as far as why I'm doing CP, it's only because I had lying around the actual values for these, okay? And I guess I should mention too, I should be using CP as 7/2 R, right? So take this, divide it by this in kilograms per mole, and you should get these values. So I think I might have accidentally said that you take the CV, but the values that I'm comparing here are for CP. Are there any other questions? Okay, so let's keep going. Now, we're not going to go nuts in this class, so for everything bigger than this, we're going to just call it polyatomic, okay? So for us, there's only one more step. This is polyatomic, where this is each gas particle is greater than or equal to 3 atoms. Okay? So, what do we do for this? Well, low temperature, still only 3. Okay? You haven't unlocked anything else. What about for medium temperature? Well, now it matters what the atom is shaped like. If instead of 2, it's 3 along the same line, then you still only have 2 rotational degrees of freedom because the third one is still degenerate. We call that a linear polyatomic. So we can have a linear polyatomic, which might look something like this, or you could have a nonlinear polyatomic. So maybe something like this. If it's one of these linears, again, you get only 2 rotational, because the third one is degenerate, but if it's nonlinear, you do get to rotate around all 3 axes. Okay? For the high temperature, it's going to add more than 1 vibrational mode. You can imagine the different ways that these could kind of vibrate against each other. Maybe they're in sync, maybe they're out of sync. Okay? There's different ways to do this. Yes, there's a way to count them. No, I'm not going to tell you what it is. It's not for us. Okay? Not for us. Okay? So I'm not going to ask you about that. I'm not going to ask you about a gas particle that has 3 or more atoms that make up the particle at high temperature. You can look up the formula. The formula is really easy, but as far as understanding how to count those, that's more challenging, and so I don't want to just throw formulas at you when I can avoid it, especially since we have plenty to play around with already. Okay? So what does this tell us? At low temperature, we get the same thing we have been. Okay? At medium temperature, you'll get 5/2 R for a linear polyatomic, and you'll get 6/2 R or 3 R for a nonlinear, and the only thing that you can say at high temperature is that you're going to be bigger than 7/2 R, okay? Because of course you have more degrees of freedom than you did before, okay? That makes sense? Okay, so let's make a little drawing of this. What's CV versus T look like? Let me make it a little bit bigger than that. So, CV versus T for polyatomic at low temp, start off at 3/2 R. Notice at very low temperatures you can't tell the difference between any of these gases. They all have the same exact value, right? In fact, we might draw as a baseline here, this is our monatomic gas. Okay, so our monatomic gas stays there. It does not have any temperature dependence. Okay? So, over here, we start to go to medium temperature. So at this point, we're at, let's say we're at 5/2 R. That would be for the diatomic and the linear polyatomic. But we could tell the difference here. We can't tell the difference between diatomic and linear polyatomic, but we can tell the difference between the linear and nonlinear polyatomic, right? Because one is 5/2 R and one's 6/2 R. So that's your nonlinear polyatomic. Okay? So this is your medium temperature range. Okay? Now what? Well, we get into the high temperature range, so low, medium, and high. At this point, the diatomic grows up to 7/2 R. This is the the diatomic. And if you're talking about the polys, who knows? Dot, 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 question mark. These are your polyatomics, okay? Does that make sense? So you notice that at low temperatures you can't tell the difference. At medium temperatures you can tell the difference between some things and not other things, and then by the time you get to the high temperatures, how many degrees of freedom there are to unlock have all been unlocked. Those could be vastly different, and you will start to notice gases behaving differently. Okay, so let me tell you real quick here, just so I don't have to come back to this. Let's take a good H2O gas, water vapor. Okay? So, does anyone know if water is linear or nonlinear? You should know. Nonlinear, that's right. Okay, you got your classic water vapor shape. So, at medium temperature, we predict that CV should be 3R, right? And CP should be 4R, just adding 1, or 33.24 joules per mole Kelvin, okay? So let's see how that fares. The molar mass per gas particle. Well, luckily I already did your H2, right? So H2 is here. So it's 2.016 joules per mole Kelvin. That's your H2. Plus, what else is in that gas particle? Oxygen. 16, oh, what am I doing? That's grams per mole. Grams per mole, grams per mole. There's your oxygen. Oxygen is element number 8, so 8 times 2 is 16, right? Okay, so if you've got 8 protons but then 8 neutrons, and if you do this, you will get a specific heat capacity of 1845 joules per kilogram Kelvin. The actual value is not even really very close, 2080, which actually is a CP of 4.5 R. Okay? So the reason why is because this is supposed to be 4R. What's with the extra 0.5? Well, unfortunately, water vapor is one of those things where we are actually not in the quote-unquote medium temperature range. The high temperature starts pretty early for water, and we're actually already on the uphill climb. Okay? So again, I said that the placement of these plateaus is not something that is always terribly convenient. I will try to keep it so that you're not awkwardly transitioning between them, but water is one of those things that often is the exception. Okay, so let's cut off there. Sorry to go a little